Hello. Good afternoon, everyone. Today, we are going to see the last point of our last chapter and also the whole switchgear and protection, that is the insulation coordination in power system. So, before that, we'll discuss what we've seen in yesterday's lecture. So, in yesterday's lecture, we've seen the metal oxide or zinc oxide arresters, right? So, here uh, this zinc oxide is nothing but a metal oxide, means mostly used metal oxide material in the arrestor is the zinc oxide. That's why these are also called as zinc oxide arresters. So why these arresters are used? So we have seen that if the over voltages are there, then we have to either divert or absorb such over voltages or surges due to, means the surge energy due to these over voltages. So for that, we are using the protective devices. These are nothing but the surge arresters, surge absorbers, right? So there are different types of such arresters. These arresters are nothing but a protective device used for the over voltage protection, right? This metal oxide or ZNO arresters are used for the protection of the line against over voltages. Okay, so these over voltages can be due to the switching impulses. Switching means you are changing any of the line, then lightning impulses, these are nothing but the lightning strokes, and some fast transient over voltages, means if there is a sudden increase in the voltage, uh, or transients, these are nothing but the transients. Okay, so we are using here this Zn0 or Zno arresters here, metal oxide arresters. Now, then we have seen the construction of this. So this is the construction of the metal oxide arrestor. That is, we are using here the zinc oxide disc. So these discs are placed in such a way that they form a stack. There is a wiring bolt, wiring nut is there, and two electrodes are there. These are the stainless steel cap, and these two are the electrodes. Okay, these two are the electrodes, and in between them, this material is provided. This is a non-linear resistor, and there is a porcelain housing. Okay, porcelain housing means the insulating, uh, there is a coating of the insulator, right? And and there are different number of discs, and these discs are placed in a stack. Okay, in a stack. Now what happens, this is also called a gapless arrestor. Why it is also called gapless metal oxide arrestor? Because actually when we are considering uh, any arrestor, that time we are using only these two electrodes. Okay, only two electrodes, and in between them there is a gap. There is a gap, and that gap itself acts as a resistance. Means what happens when under normal operating conditions, means when there is no any fault or no any lightning stroke, that time these contacts are open, means the resistance between these two is high, so that current will not reach towards the earth, right? But when that lightning stroke will be there, or hit that pole or anything, so this get closed and the current will flow through these two towards the earth, and in this way it absorbs or it diverts that surge energy towards the earth. So in this way there is a working, but here we are using, instead of that air gap, we are using here, means that gap is filled with this zinc oxide disc and which is coated with this porcelain. Okay, so right here a stack is used, and these are also called the gapless surge arrestor. Okay, zinc oxide gapless surge arrestor, because here we are using that zinc oxide metal disc, right? Uh, then we have seen the working also. Working is same like our normal surge arrestor. That is when under normal working condition, uh, the resistance between the two electrodes will be high, so that current will not reach towards the earth, means it acts as an open circuit. And when any over voltage will occur there, that time the current will flow, means that surge arrestor will act immediately, and the current will flow towards the earth, right? And the advantage why we are using these metal oxide surge arrestors, we have seen the advantages also. So under normal working condition, actually there is a leakage current flowing through that surge arrestor, but in this surge arrestor there is no leakage current. This is the advantage of these metal oxide surge arrestors. And these surge arrestors are used for voltages up to 6.6 kV, and it is used for the protection of the transformers. Okay, transformers and motor feeders also in switch gears, and their ratings is of 6.6 kV. Okay. These are some points, and the advantages are also there here. uh, Due to the high degree of ionization, high degree of nonlinearity in arrestor resistance, it eliminates the use of spark gap. Okay, means non-linear characteristic is there, therefore spark gaps we are not using there. There is it is having simple construction, and the size is also reduced, and superior protective performance, and quick response for steep discharge current. Okay, steep discharge current means if there is a highly suppose intensive characteristic is there, then that arrestor get immediately operated. Okay, then it is stable in operation, and it is having energy absorbing capacity. And if there is no surge, the flow of leakage current is low. Okay, flow of leakage current is low as compared to other arrestors. So these are the advantages of the metal oxide or zinc oxide surge arrestors. Okay. So this is important point. Asked points are there, so you do all a very small chapter. Okay. So at least one question is compulsory from this chapter. Okay. Then uh, the new point, today's new point is the insulation coordination in power system, right? So we will see here what is mean by insulation coordination. There are different methods of doing this insulation coordination. This point is also very easy. So insulation coordination is nothing but when there are over voltages, right? Over voltages occur due to the lightning strokes or some environmental calamities. So what happens? The voltage of that pole or the transmission line or the equipment get immediately increase. So if that voltage increases, it will damage that equipment, or it can also damage the line, right? And its repairing is very costly, uh, right? Because we know that there are 220 kV transmission lines, and these towers are also having six lines, such lines. right? So if that tower get affected, then whatever be the supply provided to the load, that whole system will stop there, right? So uh, to protect that system from these over voltages, we have to do something. Means we are using here surge arresters, right? Surge absorbers, right? So means different types of arresters we are using. But this is uh, means instead of using that surge arresters, means this can be used for the particular voltages, but instead of using that surge arresters, can we improve our insulation only? So that is a question, because when for the protection purpose we are using the insulation. For every equipment there is a insulation, for every conductor we are using insulation. But what happens when we are considering the long transmission lines? So can we use insulation for such long transmission lines? Is it feasible to use insulators for such lines? Yes, anyone? Then how we are protecting these transmission lines? Is there anyone in the lecture? Hello. So for the transmission lines, we are using insulation or not? Is anyone? Vaishnavi?
No, ma'am.
Sonal? Yes, anyone? Okay, I think no one in the lecture. Right now? Shivaji? Okay. So here what actually happens when we are considering the long transmission lines? So for such a long transmission lines, actually voltage is very high. That is, suppose we are using here 220 kV transmission lines, then it is not possible to use such very high voltage insulators, right? So we are using the insulators, right, for some equipments, or for some lines, right? But not for all. Okay. But we can protect if we are using the insulation of the higher value than the rated value. mm, then we can surely protect that equipment, or we can protect the line also, right? So how actually it is, that will be seen in this point, that is insulation coordination in power system. So this insulation coordination is introduced to arrange the electrical insulation levels of different components in electrical power system, including transmission network. So here, uh, we are, what we are doing, we are simply arranging the electrical insulation levels of the different components, okay, in electrical power system, including the transmission network also. So if the failure of insulation occurs, means if the insulation fails, it would result in least damage of the power system, and it is easy to repair and replace, and results least disturbance to the power supply. Means what will happen if we are considering this insulation coordination power system, means for the transmission purpose also. So if that insulation will fail, okay, uh, means after any strike of that lightning stroke, then if the insulation fails, then also there will not be that much damage to the transmission line, because there is a protective insulation. Then it is easy to repair and replace. It is easy to repair and replace, and easy to repair and replace, and results least disturbance to power supply. Okay. Uh, Means if uh, if the breakdown or damage will be less, so it can be easily repaired and replaced, and there will be very less disturbance to the power supply, right? So when any over voltage appears in the electrical power system, then there may be a chance of failure of its insulation system, right? So mm, if there is any over voltage in this system, means if any lightning stroke will be there, then there, of course, the insulation will fail there, and probability of failure of insulation is high at the weakest insulation point nearest to the source of the voltage. Means where actually that is strike, means where is that source of the source of the voltage. So near that point, the insulation will be weak, and there is chance of failure of that insulation, right? So in power system and transmission networks, this insulation is provided to the all equipment and components, right? uh, so we are providing insulation to all, okay, to all the equipments and all the components. So insulators in some points are easily replaceable and repairable, but in some points the replacement and repairing may be highly expensive and require long interruption of power. Okay, means at some points, means for example, if we consider the distribution system, so at these points we can easily replace or repair that insulation. But if we consider the transmission systems, then it is difficult to repair and replace the system, and also it is highly expensive and require long interruption of power. Okay, means if any feeder uh, is failing to supply, then it is okay. But if the whole that system get damaged, that time it is difficult, or it will take the long time, okay, for the repairing also. Means there will be uh, continuously interruption of the power, right? So this is what nothing but the insulation coordination. So failure of the insulator at these points may causes bigger part of the electrical network to be out of service. Means if that insulator fails, uh, or the insulation fails, then means that whole system gets breakdown. That is, that network will be out of service of the supply. So it is desirable that in situation of insulation failure, only the easily replaceable and repairable insulators fail. So we have to consider, or we have to take care uh, that if the insulation fails, such an insulation should fail that it is easily repairable and easily replaceable. So such insulation, if fails, then there will not be any problem. Okay, so the overall aim of this insulation coordination is to reduce an economically and operationally acceptable level cost and disturbance caused by insulation failure. So we are doing this insulation coordination. So why we are doing this? We are doing this for reducing the level or the cost of the operation, and mm, also the disturbance caused by the insulation failure. That's why we are using this or we are doing this insulation coordination, right? So in this insulation coordination method, the insulation of various parts of the system must be graded. That flashover, if occurs, must be at intended points. Okay. So in this insulation coordination, means in the there are three methods of this insulation coordination. So in these methods, means insulation of various parts of the system, okay, must be graded. Okay, graded means in such a way that if any flashover, okay, flashover occurs, then it must be at intended points. Means it should be at the specified points. It means that these points should be replaceable and repairable. Okay, replaceable and repairable. Okay, so there are three methods of this insulation coordination. First is using the shield wire or earth wire. Second is conventional method of insulation coordination. And third is statistical methods of insulation coordination. These are the three coordination methods, and we'll see now one by one here. Okay. First, that is using shield wire or earth wire. Okay. So all of you have seen the tower, right? Na? Everyone seen the transmission line tower? Yes or no? So if all of you know, just tell me how many lines are there for the transmission tower? How many lines are there? Yes. Is there anyone in the lecture? Arbaz? Kishori? Okay. So here first is the using shield wire or earth wire. I think all of you know this, right? So for this transmission tower, there are 7 links. So this is the top one, that is the shield wire, or it is also called the earth wire. Then these to one side, 3 conductors are there, and to another side there are 3 conductors, right? So this is called the double pole structure. These are the 3 phases, and these are the 3 phases for 2 sides. And actually, the conductors are uh, at the lowest end of that line, and here there is an insulator string, right? Insulator string, and this is the area which is protected by the protective devices, and here this is the protective angle. Okay, protective angle is there. So the lightning surge in overhead transmission line may be caused due to direct heats of the lightning strokes. So we have seen that when we are considering that if that lightning stroke is hitting any of the pole or any of the transmission line, so it is first searching the tallest so that it can easily reach towards the earth, right? So means whatever damage is there, that damage is also more because this transmission line voltage is very high, right? Therefore we have to protect these towers and also the transmission line. So we are using their uh, different types of arresters also, right? So it can be protected, by providing a shield wire or earth wire at a suitable height from the top conductor of the transmission line, right? So by considering this top conductor is nothing but the earth conductor. uh, Hello. So if that if it can be provided by using a shield wire or earth wire at a suitable height from the top conductor uh, of the transmission line. So what we are doing, we are using this shield wire or earth wire for protecting that transmission line and that whole tower. Actually, that uh, this is also called the neutral wire. I think in examination also they may ask you such a question, that the top line of the transmission line of the or the transmission tower is called, it is also called the earth wire or neutral wire or the shield wire. Okay. Then uh, so by using this line we can simply protect that tower, means whatever is coming under it's a protective zone. So everything is protected here. Okay. So if the conducting shield wire is properly connected to transmission tower body, okay, means if uh, we are connecting this wire correctly, okay, or properly to that transmission tower and the tower is properly earthed, then direct lightning strokes can be avoided from all the conductors come under the protective angle or earth wire. Right. So you may also know that these transmission line towers are also earth. Right. So if we are using that shield wire or earth wire, then it is protecting all lines, that is all transmission lines which are coming under its protecting zone or under the protecting angle. Okay, so there is this one central line, and from that line it is making the angle, that line is making the angle, and in between that angle, so whatever is coming, everything is protected from the lightning strokes or from the over voltages. Okay, so it is used in electrical substation to protect different electrical equipment from lightning strokes. Okay, so this earth wire is also used in substations for protecting different electrical equipments. Okay, uh, so this is the use of that shield wire or earth wire. Okay, then the second method. So everyone got this? Everyone got this? Yes or no? Okay. Then next point is the conventional method of insulation coordination. Okay. So this is the second method of insulation coordination. First, we have seen that is the shield wire or earth wire protection. Then second is the conventional method of insulation coordination. So in this conventional method, what actually we are doing, we are providing the insulation there. Okay, for the lines or for the equipment. So the team may suffer from different level of transient voltage stresses, switching impulse voltage, and lightning impulse voltage. Right. So this electrical power system is suffered from the transient voltage stress will be there. Then switching impulse means due to switching the voltage sometimes get increased, and lightning impulse voltage is also there, means it is due to the lightning strokes. Right, means these voltages are getting increased many times or frequently. Right, so we have to protect that system or the equipments. So the maximum amplitude of transient over voltages means uh, uh, it is the maximum value of the transient over voltages reach the components can be limited by using protecting device like lightning arresters in the system. So under these conditions, right, that is the switching impulse voltage or switching impulses or lightning impulse voltage, etc. So that time what happens, the voltage get increased to a high value, and we have to protect the systems against such voltages because these are the beyond rated value. Right, and for that purpose we are using the arresters. Right, for this purpose we are using here arresters. So if we maintain the insulation level of all the power system component above the protection level of protective device, then ideally there will be no chance of breakdown of insulation of any component. Okay, means what happens if we uh, level, uh, so that it is above the mentioned level of the voltage. Okay, above the mentioned level of voltage means uh, the protective device insulation level should be higher than the voltage level, which is the highest voltage level. Okay, then the chances of the breakdown of the insulation will be very low there. So since the transient overvoltage reaches at the insulation after crossing the surge protective devices, okay, means if the transient voltage will reach at the insulation, okay, when it will reach at the insulation after crossing the surge protective devices, okay, means of course there will be surge arrestor, and it will have the amplitude equals the protection level. Okay, now that time means the transient to when the transient over voltages reaches at the insulation after crossing after crossing the surge protective devices. So they will have the amplitude equal to the protection level voltage and protection level voltage impulse insulation level of the components. Okay, insulation level of the components. So generally the impulse insulation level is established at 15 to 25% above the protective level voltage of insulation, right? So uh, uh, means the impulse insulation level means when any that switching impulses or lightning impulses will be there, that time that level of voltage will increase, but we have to use the insulation which is having a protective value, and that is more than the rated. Means it is 15 to 25% above the protective level voltage. Okay, means whatever be the protective level voltage, means suppose or beyond that 11 kV. Actually, the variable we are considering, but beyond that voltage, your line will get damaged there, or it will get break there. So, we are using insulation of such a value that if the voltage increases more than the rated value, up to 15% to 25% of the given protective level of the device. Okay, of the device. So here the characteristic is given, right? And this characteristic is of peak voltage versus time. That peak voltage is in kilovolt and the time is in microseconds. So here the characteristic is shown. The characteristic A, this the characteristic A is the protection level voltage of the protective device, and the characteristic B is the impulse insulation level of equipment to be protected. Okay, this is the impulse insulation level of equipment to be protected. Okay, so from these characteristics, uh, can anyone tell what you studied in this point? Conventional method. Yes, anyone? Sagar? Pooja, Pratidnya, okay. So here you can see from this characteristic that this is the protection level voltage of the protective device, and this characteristic B is showing the impulse insulation level of the equipment to be protected. Means the insulation level is having higher value of the voltage, that is the 15 to 20% above the protective level voltage of the protective devices. Okay, means the insulation will have some more value. The insulation will have some more value than the actual value of that line or of that device. Okay, then the third method of the insulation coordination is statistical method. Okay, statistical method of insulation coordination. So what is mean by this statistical method? So in this statistical method, we are considering uh, it is the graph of required number of discs of insulator and over voltages in per unit. So it is the required number of disc insulator in different over voltages, right? We know that when we are considering the insulator or uh, in between that transmission line and that tower end or that tower point, we are connecting the insulators, and these insulators are having discs, right? So they are in stacks. These discs are mounted in a stack and they are forming one string, right? So you may have studied in power system the string efficiency, etc. So there are actually number of discs, and these discs are having some particular magnitude, right? Means that voltage. One disc is of 11 kV generally, right? Now, right or wrong? So who is present in the lecture? Please unmute. If anyone is present, unmute yourself. Yes, anyone? Means out of these 31 students, can I say no one is present? Can I mark absentee for all? Swapnali, Shubham, okay. So here uh, we know that when we are considering that insulator string, that time one disc is of 11 kV. So how many number of discs are there in one string? From that we can find the voltage of that transmission line, right? Or voltage of any line, right? Means for example, if there are 6 discs and one disk is of 11 kV, then the total voltage is 6.6 kV, right? So in this way, you can find the voltage from that disc only, that is from the insulations only. So here in this graph, actually this is the statistical method of insulation coordination. So in this graph, uh, uh, on this x-axis there is over voltage in per unit, right? Over voltage in per unit, and on y-axis there is required numbers of this insulator. Okay. uh, so there how many days we are using for the insulation purpose there, these are given. Okay. So in this statistical method of insulation coordination, at higher transmission voltages, the length of the insulator string and the clearance in air do not increase linearly with voltage, but approximately to V raised to 1.6, right? So when the transmission line voltage is very high, uh, the length of the insulator string, okay, insulator string, and the clearance in air do not increase linearly. Means means the length of the insulator string and the clearance in the air, they both are not increasing linearly with voltage, but approximately to V raised to 6. Means they change with V raised to 1.6, right? So increasing number of disk is only slight for 220 kV system, with the increase in the over voltage factor from 2 to 3.5, right? So if we want to increase the number of discs, so this increase in number of discs is the increase in number of discs is only slight or less for the 220 kV system. So with the increase in over voltage factor from 2 to 3.5, but that are but there is a rapid increase in 750 kV system, right? So uh, means if we increase the voltage, then number of discs for required for the insulation purpose also increases there, right? Then uh, the while it may be economically feasible to protect the over voltage lines up to an over voltage factor of 3.5. Okay. So if uh, we are considering this as economically, okay, then for protecting that voltage, okay, or to protecting the lower voltage lines up to an over voltage factor of 3.5, it is not economical, and also it is not feasible, okay, because in the higher voltage systems it is switching over voltages that is predominant. So switching over voltages are predominant there, and however these may be controlled by proper design of switching devices, okay. So we can control this. So in this way there are three methods of this insulation coordination. That is first is the by using earth wire or shield wire, then second is the conventional method, and third is the statistical method, right? So by using these three methods we can provide the insulation coordination to the system or to the equipments also. Means where actually there are different chances of the failure of the insulation, there you can provide the insulation which can be easily repairable and replaceable, right? So if we provide such insulation, then the cost of repairing and replacing of that line will also decrease. Means that will protect the system from the over voltages. Okay, so if we are using the insulation or if we are doing the insulation coordination, right? So in this way we have studied all the points we have covered here from this last chapter. Okay, so the unit contents were causes of over voltages we have seen, then surge arresters, surge absorbers, metal oxide arresters, and insulation coordination in power system. All 4 points are covered here, and in this way our seventh chapter is also over. Here our whole syllabus of the switchgear and power system is completed, right? If you have any doubt, you can ask me. Is there any doubt? If anyone want to ask anything, can ask me. Yes, anyone? Srishail, Deepali, any doubt? If anyone is present, you can ask. Shantanu, okay, if you don't have any doubt, uh, then I declare here that our syllabus of switchgear and protection it's over here, completed. I'll upload all the PPTs, all the remaining PPTs in Drive. Then all the assignments are already given. Everyone solve these assignments. Okay, and for uploading, I shared one form, Google form for one assignment only. So I'll share that form, and only our practicals are remaining. So we'll cover these practicals in this week only. Okay. So whatever kits are available from that kits, will cover the practicals, right? So for now, thank you all and have a nice day. Thank you. I'm ending lecture now. Thank you.